I want to tell you today about some things I've been thinking about with respect to probability and intuition. So, my research for the past 10, 15 years or so has involved a lot of combinatorics, and probability, and theory of computing, and has brought me into contact with a lot of statistical physics as well. And in statistical physics, we often see a very interesting phenomena that make us think about our intuition about probability. And actually, the picture I have on my slide here is an example of that. Let me show you a little bit more. Some of you have seen this, I know. But here's a very cute little theorem, the Arctic Circle theorem. And it talks about a random tiling of this shape, which they call an Aztec diamond. And the tiling is by dominoes. And in this particular picture, the horizontal ones are colored yellow or blue according to parity, and the vertical ones are red or green according to parity. So that's a uniformly random tiling of a Aztec diamond, and so far nothing remarkable about it. But if you look at
what is parity?
Yeah.
Okay, parity. Yeah. So if we label all the individual squares according even or odd, color them like a checkerboard.
Rectangles?
Just the squares. If we color the underlying squares,
yeah.
red or say red or black like a checkerboard, then the parity of a rectangle will determine, a horizontal rectangle will determine whether its left half is it a red square or a black square. And so there are really four types of tiles looked at this way. And there's a tendency for the to have green tiles at one end and yellow tiles at a second end and blue and then red. And you don't see it in a small example like this, but take a look at this picture. So this is a uniformly random tile. And don't ask me how to get one, because that's another whole story. And you'll notice that it appears to be random in sort of a circular region inscribed inside the diamond, and then but regular outside that. And that was something that Prop and these others noticed. And in this case, not every case, they were able to prove that this really happens. This is a bigger picture even. They were able to show that take a uniformly random tiling of a very big diamond, that it will be random inside an inscribed circle and completely regular outside. Right? Why? Yeah.
And somehow the complication is that you have to fill every little
That's
square.
right, you have to fill everything, and it's easier to fill stuff with the right parity at each end. But then at some point, it gives up trying to do it the right way and it wants to do it the random way. And it's kind of remarkable that it gives it up at such a sharp boundary.
Even within the circle, there's a gradient. Okay.
That's right, even in the circle there's a gradient.
If you rotate the diamond by a small angle, perturbate a little bit?
There are other phenomena like this now known. There's another one where you get an 8th degree curve. That's now called the Arctic Circle theorem. And there's lots of work by Andrei Kunkov, for example, and my collaborator Rick Kenyon from Brown. We now know a lot more about why these things happen and how they happen.
What does random mean? What's the process with tiling? What's the random process?
Abstractly, what's going on here is that there's some enormous number of ways of tiling this thing. And one of these ways is chosen uniformly at random. Okay? The technical problem of how to get one of these uniform random things is it requires using some fancy mathematics.
I mean, you just count every possible tiling.
In principle, you count every possible tiling and you pick one out, and that's it. Isn't that remarkable? Yeah. Well, the stuff I'm going to talk about today is mostly more elementary than that, but also stuff which I've kind of picked out, which tickles my intuition. Now, your intuition in many of these cases is going to be better than mine. So if something that I claim looks unintuitive, you think it looks obvious, don't worry about it. It just means that you're smarter than I am. Okay. All right. So now, I teach probability at Dartmouth. And I like to start by shaking my students' belief that they understand what probability is. So I've invented this story which I have to pass to you. And it's about 3 academics who are sitting around a table and they're discussing the question of whether there is intelligent life outside, off the Earth, outside the rest of the universe. And they have an argument. One guy says, oh, it's 1,000 to 1 or 1,000,000 to 1 in favor of it. There's a huge universe out there. We're discovering new planets all the time. Obvious there's going to be more life out there. And, you know, and maybe the next guy says, I don't believe it. Just think of the amazing things that have to happen for life to occur. It's a whole chain of things that make it exponentially unlikely. And we have to remember that just because we're here, we can't, if we weren't here, nobody would be here to think about this problem, so, right, you know this argument. Okay, and maybe a third guy says, I don't know, I mean, we really don't know, so how can we assign any kind of extreme probability? Let's go on 50-50, you know. All right, so in the middle of this discussion, one of the professors rubs a lamp by accident and a genie appears. The genie thanks them for releasing him and says, ask me anything you want to know, I will tell you. That's quite a gift, right? This is very nice. So the professors think about this for a while, and then they say, okay, we want to know what is the probability that there is intelligent life elsewhere in the universe. Okay. So of course the genie says, oh, of course, I'll tell you whether there's intelligent life out there in the universe, and the answer is, the professor says, no, we don't want to know that. That wouldn't solve our problem at all. We want to know what is the true probability that there is intelligent life elsewhere in the universe. Okay. So this usually gets them thinking. There's the stymied genie right there. Okay. A word about probability, where it belongs in history. I like to tell my students that many historians trace it back to 17th century France, some to a particular problem, some to this problem that settling gambling debts. I mean, gambling has been around for a long, long, long time, and people needed probability to understand it better. The concept of statistics wasn't really around then, but now, of course, probability is the foundation for statistics, as Yuri mentioned, and you know, you just have to sit and imagine where we would be. I mean, we like to think we understand the universe. I come from a family of physicians, for example, right? And physicians have a whole theory about disease and the body and all the rest of the stuff. But in fact, almost everything they do is based on experimental evidence and the statistics thereof. I mean, many medicines, they have no idea how they work. Other medicines, no idea why they don't. It's a hit or miss proposition, as I'm sure many of you have run across. Remembering a story that my parents tell about medicine. This is a little off the record. For amusement. A guy goes to his doctor with a bump on his elbow. And the doctor says, I think you need to put a cold compress on that. It'll probably go away after a while. So a couple of weeks later, he runs into the guy in the street. He says, I see your bump is gone. That cold compress really worked. And the guy said, well, as a matter of fact, I went home and I was putting this cold compress on when my housekeeper came up. And she said, that's not the kind of thing you put a cold compress on. You put a warm compress on there. So I put a warm compress on it and eventually it went away. The doctor said, oh, that's funny. My housekeeper says cold. Okay. Now, so I think most most people sort of felt for a long time that probability was a construction of humans. After all, we invented it, right, to explain gambling, and then later on to talk about statistics. But quantum mechanics has come along and seems to tell us that probability actually exists independent of humans somehow. And we have a theorem, which I won't go into now, which says that you can't really explain what happens in the quantum world by hidden variables. I mean, it really is, particles have what people call free will. They really don't know where they're going next. A fascinating subject, one of many that we won't be getting into today. What I'd like to talk about is how humans deal with probability. And let me start with something that I bet some of you have seen before, the Linda problem. Take a look at this and tell me if it's familiar. So Kahneman and Tversky made big stuff out of this, including a Nobel Prize for one. And Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, participated in anti-nuclear demonstrations. Which is more probable? Linda is a bank teller. Linda's a bank teller and is active in the feminist movement. Okay. Now, I'm not even going to take a poll here because you guys are way too smart. But Kahneman and Tversky found that typically 80 to 90% of the people who are confronted with this problem think that Linda is a bank teller and is active in the feminist movement is more probable. Okay? And we know that that can't really be because that requires more things to be true than the first one. Okay? But I've noted that as smart a guy as Stephen Gould found this very seductive. Now, there have been objections to this, and I won't go into details on it. But I want to show you why this is not exactly the kind of problem I'm interested in. I will leave this problem to Kahneman and Tversky and the psychologists. This has to do with, I think, the fact that people are not used to setting up sample spaces. Okay? Those of you who have actually dealt with probability or taught probability or read the introduction to the book, that's all I really intended you to take a look at, by the way. How you set up a probability problem is very important. And when you just ask, this is a description of Linda, is it more probable this or is it more probable that? You haven't really set up a very precise experiment. What is the experiment? I mean, it's not unreasonable that a person asked this question might envision meeting a bunch of people at a party and looking for Linda because someone has told him about Linda. And he's introduced to a person who was a bank teller and introduced to another person who was a bank teller and active in the feminist movement. And naturally says, oh, this one is more likely to be Linda. Okay? In fact, if you ask the question this way, nobody has a problem. Just say, okay, you've got 100 people here. How many fit this description? How many fit that description? And virtually everybody seems to get right that fewer people fit the second description. Here's some other examples. Here's a problem that Martin Gardner made popular. Although maybe it was popular for years before that as well. Mrs. Smith has 2 children. One is a boy. What is the probability that the other? Who can tell me what is the answer to this? What's the probability the other child is a boy?
It's more than one. It's more than a half.
It's more than a half. 2/3. The answer is supposed to be 2/3. Okay? And most people answer half. And then you explain to them, you go through all the mathematics, it has to be 2/3. But are they really wrong? Well, if you think about the ways you could learn that one of Mrs. Smith's children is a boy, practically all of them put you into a question where the answer actually is half. If you run into one of her kids and it's a boy, the probability the other one is a boy is a half. if you see her buying clothes for a boy, she's buying clothes for one of her children, you know one of that children, the probability the other one is a boy is a half. It's only, it's almost hard to put together a situation where you somehow find out that she has at least one boy and is equally likely to have boy, 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 girl, or girl, boy, and therefore the probability that one is a girl is 2/3. If you make a very specific question of the same, this is really the same question in a different context. Okay, we have an urn which contains a two-headed coin and a fair coin, and we reach into the urn and we draw a coin out of it, and we flip it. It comes up heads. We ask the question: what is the probability there's a head on the other side of this coin? Okay, now it's a theorem that the probability there's a head on the other side of this coin is 2/3. There's really 3 heads you could be seeing, and 2 of them have a head on the other side. And if you have difficulty convincing people of this, or doing the Monty Hall problem, or various other things that you've seen, often if you do a reductio ad absurdum argument, you can make people see it, right? So suppose, for example, you take this coin out of the urn, and you flip it 10 times, and it comes up head every time. And then I think you'll get your audience to agree that there's now a substantial inference that this is probably the two-headed coin that you picked. And now you just have to convince them that the inference exists already after only one flip. Bridge players know about this because there's I don't know any of you play bridge, but there's a concept called the principle of restricted choice that comes up a lot in bridge. And the result is that the bridge players have less of a problem with the Monty Hall paradox than mathematicians do. Well, there's a problem with that problem. Okay, let's go to Las Vegas and do some gambling. Let's back to the origins. Here's what I like to throw at students, and maybe you like it too. Okay, we have a friend, Andrew, who decides to make 105 successive $1 bets on the number 21. It's his birthday. He's in Las Vegas. There he is. There's a roulette table right there. He makes this decision, and he goes ahead and he makes 105 successive $1 bets. And now, well, you guys know how roulette works, right? You, if it doesn't go up with your number, you lose your $1. If your number comes up, you spin this ball around here. If the number comes up, then you win $36. That would be a fair game if there were 36 numbers. But there's actually 38 numbers in most roulette wheels in Las Vegas, although I'm told that at some places you can get it with only the 0 and not the double 0 in Las Vegas, which is the Monte Carlo standard. Okay. Either way, like all games in Las Vegas, it's rigged against you. So on average, you're going to lose about a nickel every time you play. Okay. So the question I'm going to ask is, roughly speaking, what's the probability that our friend Andrew comes out ahead after 105 straight bets in this game? So, okay, I don't want you to be doing any calculations here. Just, how many think the probability would be above 10%? I've got a few takers above 10%. How many, anybody here think it might be below 1%? No, maybe. I got one taker. What's the answer? Good news and bad. Yes. Turns out the probability it comes out ahead is better than 50%. Now, this sounds a little odd to many people. Wait a minute. You know, does that mean that Andrew has Las Vegas by, you know what? No. Why? He still has expected winnings minus $5. The reason is, see, 105, see, the problem is if he wins 3 games, he wins $108. It comes out $3 ahead.
Well, why? He's lost 100 on all the other ones.
He's lost one for all the...
So if he does it 100 times, and he wins 3 times, he gets 108, and he spent 102 on all the other ones that he lost.
No, we spent 105.
Wait for chances to get that third win.
Right. The dollar goes in, the 36 comes back.
don't get 37.
Yeah, you don't get 37 when you get 36 only. So so he wins $3, and that's a very common outcome that he'll win 3 times, but it's also pretty common that he'll win only 2 times and lose a lot of money. So the point about this here is that there's a big difference between probability and expectation, and these things are often confused. One thing I like to tell my students is suppose you think that the probability that global warming is man-made and about to destroy us is 5%. Does that mean that you should scoff at the people who believe in global warming? Well, you might also consider what is the expectation if we don't do anything about it and it really exists? What is the expectation if it doesn't really exist but we do something about it? And you might think, okay, well maybe this is something we should do something about after all. The difference between expectation and probability. Okay, since we're in Las Vegas,
That's a possibility.
so let's suppose that Andrew has won his $108, and he's offered the following game. You know, if you're a smart person and you want a random number between 1 and 6, and you have a die, you roll it. Okay. But you know that's too easy. Here's another way to get a random number between 1 and 6, but it's not uniformly random. Roll 6 dice and count the number of different numbers that appear. Okay? So here's 6 dice. I happen to roll them, and there I did. I got a couple of 5s, a couple of 4s, a 2, and a 1. And if this actually is the roll, Andrew wins $1. Okay. If he rolls any other number, he loses $1. And now the question is, how long can he expect to play this game before he loses his shirt? Okay. So clearly, he's got $108, so he can play at least 108 turns, and he's going to be winning some of those times. So I would say maybe 500 games or something like that.
He wins one, okay, so...
He wins $1 if he gets 4 different numbers.
Okay. So
He loses $1 if he gets 5 different numbers or 2 different
he doesn't have
numbers.
to pay each time, like in the roulette, to put some money.
It's either plus,
$2.
It's either plus or minus.
it's plus or minus 1 that he gets, right? Yeah, plus or minus 1. So if this is a different number, if this is a fair game, if it's a 50-50 game, then it's a fair game between plus 1 and minus 1.
But does he choose different numbers each time?
He doesn't have to choose anything. He just rolls the dice and counts the number of different numbers that appear.
Well, you would tell us the
Does the
problem.
number that he chooses going to be different?
Oh no, it's always a 4.
It's always 4.
Always
But
4.
Okay.
With
Well, that
his
changes.
odds, he never makes
changes
enough
considerably.
to do much at all, right? So it's just
You would think so, but it turns out that his expected lifetime in this game is actually infinite, and that is because the probability of rolling exactly 4 different numbers is better than 50%. You're more likely to roll a 4 in this game than you are to roll all other numbers combined. Okay? And now, even though you know that this is not a uniformly random way to roll a 1, 2, 3, 4, 5, or 6, it's still a little surprising, isn't it, that the 4 stands out and eclipses all the other numbers together? Yeah, one of those great things. I found this by accident, teaching probability. I assigned the question of computing this thing as a combinatorial exercise. And it is an amusing combinatorial exercise, which I highly recommend. And you will discover it's a little better than 50%.
I'm sorry,
Yes?
what was uniformly, not uniformly random, did you explain
Yes. So
the question?
uniformly random means that every possibility has the same probability.
You
So,
mean 4, 3, 2, 1, here?
right,
Oh,
right. So if I roll a single die and it's not,
It's a failed die.
yeah, it's a real fair die, then my probability of rolling any one of the numbers 1 through 6 is the same. But this technique for getting a random number is, as we now see, very far from being uniform. If you had a die that came up with 4, as much as this procedure comes up with a 4, it would be noticeable.
So if it's less than $108, it wouldn't be a
No, even if he starts with only $1, anytime you play a favorable game, there is positive probability that you will never go broke.
Okay, so one positive probability, but your expectation here is.
All you need is positive probability of something being infinite, and it's infinite, and it's automatically infinite on average. The converse, as you know, is not true. It's one of the things that you really have to get used to is that you do have cases where something has infinite expectation, even though it's always finite. And that would happen here if the game were exactly fair. So if all you do is flip coins, and you win $1 every time it comes up heads, and you lose $1 every time it comes up tails, and you start with anything, $10, okay, then you will certainly go broke. But the average amount of time it takes you to go broke will be infinite. One of those weird things. Very hard to get used to.
What's the chance to go broke starting with $108?
In this game, you start with $108. That's a good question. I have to work that out. There's a substantial chance that you will go broke, because it really is only a hair over 50% for rolling that 4. Yeah. But there's a substantial chance you won't, for sure. Okay. Of course, yeah, I have to give you the caveat. Since this game is favorable, this is an apocryphal story. Here's a favorite problem. Some of you have seen this before. Maglianti brothers, the Car Talk boys, enjoyed this one as well. And but let me run through it for those of you who haven't seen it. 100 passengers board a jetliner. The first guy on managed to lose his boarding pass. Now, that tells you that the first guy on was probably a mathematician. Because to lose your boarding pass between the time you showed it at the gate and the time you actually got on the plane requires special training. Okay, so the hypothesis is that this mathematician takes a random seat, uniformly random seat on the plane, and after that, every passenger who gets on and finds his own seat occupied takes a random seat instead. Okay, and the question is, what is the probability that the last passenger gets his own seat? And so this is a fun puzzle. It both has the property that the answer is counterintuitive, which I like, and also the property that there is a nice way to see it that makes it obvious that it's true. Okay, who knows the answer?
1 over the number
1 over 100. That's 1 over 100 is a very reasonable answer. Yeah.
Are we allowed to guess?
Yeah, I guess.
1 over E.
1 over E. That's another very good answer. Okay, I like that. I like that. But you know it won't be exactly 1 over E because this is a combinatorial problem, right? It's got to be rational. Right? It's actually very rational. It's actually a half. Okay? That's higher than you probably expected. But why? Because if you think about it, that last seat, to whom does it belong? Right? Could that last seat belong to passenger number 37?
No.
It can't, because if that seat was unoccupied when passenger 37 came on, he would have sat there. He sat there. Yeah. He was sitting there. Okay. And yeah, so it has to belong to either him or the first guy. And since every random choice has treated those two seats equally, it must be a half for each. And now, here's a problem which has some similarities to that, but the main dissimilarity is that I'm not going to tell you the answer. Well, I'm not going to tell you the answer with a proof for this one, because you guys need something to do on the subway on the way home. Okay, a fleet of flying saucers comes to Earth, and they choose a particular household to beam up for experimentation and analysis. And the house happens to contain 3 men and 5 women. So, what happens is a saucer will come along and hover over a house and start beaming people up at random. Okay? So far, everything is clear and commonplace, right? And, okay. However, the Zablosians observe strict separation of sexes here. They won't be taking any males and females back on the same saucer. So the idea is that they beam, maybe they beam up a woman, and then they beam up another woman, and then they beam up a man. So they put the man back and take off with the 2 women, and the next saucer comes in. Okay. Maybe they beam up a man, and then they beam up a woman, put the woman back, and just take off with the 1 man. Okay. And so is it clear what the procedure is? You may have use for this someday. What is the probability of the last person to be beamed up as a woman? Okay. A reasonable guess would be 5 A's. Maybe 1 over E is correct. Okay. I'll let you think about it, and maybe if there's time later, I'll take a little poll. Okay. Here's one that works especially well on mathematicians. So the non-mathematician scientists in here have a better chance. Maybe all of them, it's true. Okay, before you are 2 urns. Urns are one of those funny objects, right? They come up in just 3 professions. Archaeology, and the undertaking business, right? And probability theory. So here's my 2 urns, and here are my $2. And they're actually supposed to be inside, but I want to show you that they're there, right? So and what we're going to do is we're going to toss these dollar coins up in the air, and they're going to land at random in these 2 urns. Okay, every coin lands in one urn or the other. But the catch is, these are magnetic dollars, and they're attracted to the urn that has more coins in it already, in proportion to the number of coins that are in the urn. Okay, so right, so if there's 10 coins in the left urn and 5 coins in the right urn, then the next coin will land with probability 2/3 in the urn with 10 coins, and 1/3 in the urn with 5 coins. In the beginning, since there's a coin already in each urn, the first flip is 50-50, and the second flip will be 2-1 for one or the other, and so forth. Okay. Now, I want to see if I can make some money here. So here's what I want to know. There's $1 million in the 2 urns at the end. And one of these urns will hold fewer coins than the other. Well, maybe not, but probably one of these coins will hold fewer, urns will hold fewer coins than the other. And I want to know, how much will you pay me in advance for the contents of this lesser urn? Okay, so think about it for a minute. Think about it for a minute. And remember, there's $1 million at stake here. Raise your hand if you're willing to pay me $1,000 for the lesser urn. $1,000. There's $1 million. I have one taker. Okay.
Do we get the other one?
Well, I'll talk to you afterwards. No, that $1,000 entitles you to the contents of the lesser urn. You don't get the urn itself, which might be valuable.
The chance is there 1 in 1,000 chance that it'll take 1,000 trials before it flips one way or the other?
I mean, okay, right. $1,000 is not very much money to risk for possibly. I mean, there could be $500,000 in that urn, right?
No,
there could be
the first one goes into 1, then the second one with probability 1 goes into the same one, because B is 0.
No. We start with a coin in each.
Oh, 1 in each.
We start with a coin in each. It's not a trap here. We start with a coin in each. So it's perfectly possible that we could have $500,000 in each urn. Right.
So the next time.
We have another taker for
I just
$1,000.
want to point out that this models some real life situations. For example, you have, say, Android and Apple, and people designing apps, and app designers are likely to design an app which is whichever is more popular.
Oh, absolutely. Oh, yeah, no, this comes up quite a lot. This comes up quite a lot. It also comes up in,
I want to take it back.
in card play and shuffling. I might get a chance to say that. So, all right. We've got 1,000. How many are willing to pay?
No,
I got another 1,000. How about 100?
Oh,
$100, right? You could be making $500,000 here.
Yeah,
Okay, you're frankly,
No, no,
how much
I
are
don't.
you willing to
No,
pay?
because the
Yeah,
second
but
one.
you haven't made a comparison. No, so this means that you things into
Yeah, you pay me that money in advance, and then we make the experiment, and you get to keep whatever in the small.
No,
Because
I-
they'll actually pay you a tiny fraction of a cent in advance, because why would it pay me?
Well, I'm not going to sell it to you for that.
Yeah.
Why not? You haven't said that.
Well, all right, I just suppose I did. Then would you figure it out?
What's the most?
All right,
Oh, yeah.
all right.
No,
Usually,
I do take it back.
you can take it
Oh,
back.
yes.
Yeah, but he said he did. I'll pay this down.
Oh, all right, you took it back, but I got 2 other takers.
Then you can reconsider.
Which only have one
Some sort of
urn with
explanation.
fewer coins.
Okay,
So the next
are you ready?
time-
Yeah, okay, good.
Okay, yes. On the average, that lesser earn is worth $250,000.
Wow.
Okay, as a matter of fact,
That's amazing.
amazingly, the amount of money in the lesser earn is exactly uniformly random between $1 and $500,000. Right? Every one of those numbers has probability exactly 1 over 500,000. Okay, and that's a little surprising to many people. Yes.
That runs counter to what Sylvan was saying, because you're saying you don't get a winner take all.
Well, yes and no. Okay. The point is that if we didn't have the magnetic attraction, then we wouldn't be getting anything like a uniform distribution. We would be getting a huge spike in the center. We'd be getting 499,000 something in one urn and 500,000 something in the other urn. And so the magnetic effect is enormous in bringing this spike down to a level platform. Okay. Now, I have a favorite proof that this is true, but I don't know if I have time for it. So, again, I'll hold it for the end, and if you want to hear my demonstration of it.
The sum of the series, 1 over n, is it's divergent.
That is correct.
And that's probably it, basically.
I wouldn't say so, but I will say the following. Those of you who are not willing to bet much, we're also pretty close to being right in another sense.
Well, if you took that series and you uniformly randomly deleted terms, it would still be divergent.
There's
That's
not a
true.
series.
And that's
That is true, but this is still a slightly different problem. Okay. All right. So if you were offering me less than $250,000, let me explain why you were still not far from being right. If you change the probability ratio to just a little bit, make it a little bit stronger than A over B, this might happen in the internet situation that was postulated before, right? It might be that we've seen this phenomenon. For those of you who are old like me and you saw the battle between Beta and VHS when the videotape recorders first came out, remember? And we knew that one of these guys would eventually win out and eclipse the other, and that would be the end of that. And that's exactly what happened. Maybe it happened because the mathematical ratio was just a little bit more than this A over B. If you do this, then in fact, one urn will eventually get all the money. And
This 001 means that eventually is very far down the line, whereas if you changed it to 1.1, that eventually would be irrelevant.
You're exactly right, Peter. Okay, so Joel Spencer showed me a beautiful proof of the latter part. That's a young picture of Joel, that many of you know because he's an NYU New York colleague here, not very many blocks away. And that's George Polya. The urn I showed you is known often as Polya's urn or Polya urn. Okay, good. What else have we got? Oh, this is like hot off the presses. I devised this problem based on a problem. People send me puzzles all the time. And I was sent a rather complex puzzle about rolling pairs of dice. And And I saw something in it I thought I could make a simpler version of it. I'm just going to roll one die. And Alice and Bob are going to do this until one of them is happy. What does it take to make them happy? Well, Alice wants to see all the faces. Alice is waiting until she's seen all the numbers. Okay? Think of her as waiting for a straight. Well, okay, you play poker, you know straight is 5, but we want to see all 6 values here. And Bob,
But it keeps being rolled, there's no...
we just keep rolling it until one of them is happy.
Right.
And so if this happens, Alice is happy. Bob wants to see the same face 4 times. So Bob is really rooting for a lopsided die.
Plus any 2 others.
No. It could happen the first. It could happen the first 4 rolls.
Oh, it's one die.
We're rolling one die. We're just we don't have. They don't have to be 4 in a row. But eventually, in fact, you know that eventually you will see 4 of a kind because
19.
if you roll the die 19 times, you're guaranteed to see 4 of something. So if Alice isn't happy by then by the time we make the 19th roll, we're guaranteed that Bob will be happy.
So the Alice one is just that all the different numbers have to appear at least once in the
That's right.
sequence.
Yeah.
And the Bob 5
Once
sounds.
the 6th number appears, she's...
No, one.
Is that any face
Any?
or 5?
She has to see.
No, Bob, is it any face?
Any face.
Any face.
Okay, 4 of any face. This happens to be 4 5s, but I had to put something up, right?
Okay.
Okay, so I don't know. I won't poll you, but I think most people would want to be Alice in this game. It feels like a lot to ask for 4 of a kind before you see all 6. But in fact, Bob will win this game most of the time. And in fact, for those of you who are probabilists, we have something called stochastic domination here. At every point in the game, it's more likely that Bob will have what he wants than Alice will have what she wants. And this, I'll show you another example of
The
this.
first 5 numbers come up different.
What?
He's still bigger. The first 5.
No. I didn't say in every circumstance. I said it every time. So yes, if the first 5 numbers come up one at a time, then Alice will be a favorite to win. But if you just ask the question, who was more likely to win if there's a win at 6 rolls, it's more likely to be Bob. And it's actually not hard to prove this without doing a complex calculation. Again, I won't do that here, but there's an argument you can do in your head to see that this is really going to work. And what's going on? The intuitional point that I'm making here is one that you've probably seen in other circumstances, and which is that random is not as fair as most people think. Okay? Not as fair. It's not as uniform as most people think. Many of you have heard that if you do a probability list, you can run this experiment, you can tell all the kids to go home, and those whose mom's car has an odd numbered license plate can flip a coin 100 times and write down the results. And the others can write down what they think is a random sequence of heads and tails, and they all bring their papers back to class, and you can tell which ones were the real random and which ones were the fake. And do you know how?
The real random is more regular.
The real random is less regular. The real random has longer runs. The real random has longer runs than people expect. If you ask someone to write down a sequence of even just heads or tails, 10 of them or something like that, they'll almost never make a run of 4, but in fact, you're quite likely to see a run of 4.
It was done by Tukey, right? Because he asked people to generate random numbers. The power spectrum got a peak at the Nyquist.
That's right, exactly.
Will you repeat that question, what he just said?
I will, go ahead.
The John Tukey did this experiment where he asked people to write down heads and tails in random order. After they had done that, he took the power spectrum and found that there was a peak at the Nyquist frequency, which meant that people had alternated heads and tails because they thought that was random.
There's another example of that. If you ask a basketball player, they will always tell you that there are times when they're hot and times when they're not with respect to foul shooting. But my ex-colleague Lori Snell and others have done statistical studies, and this feeling is not borne out by the statistical studies. It actually seems to be slightly more likely that a typical basketball player will make the next shot if he missed the last one than if he got it. Yes?
There's an alternative experiment where people were asked to create an unpredictable sequence. So it's much more nearly random.
That's interesting. An unpredictable sequence.
Yeah, one which an adversary can't predict what the next
the difference between random and unpredictable is very interesting. And so I and one of my colleagues, Yuval Paris out of Microsoft on the West Coast, and some other folks have been interested in unpredictable walks. You want to take a walk which has property that you can't predict where it's going to be k steps later. And it turned out this is a very subtle mathematical problem. You don't do it by taking a uniformly random step at each time, because that doesn't move around fast enough. And so we have a fun. Yes, Pierre?
I don't even understand what it means to say you can't predict. Who are you?
You are a submarine captain. Okay, you are a submarine captain. And you've just been, you tried to torpedo a ship, but you've just been depth charged by a destroyer. And so you went down, but now you have to come up again. This is the old days, you're not a nuclear sub. You have to come up again. And you want to be in as unpredictable a location as possible. Okay?
Uniformly distributed?
Well, maybe uniformly distributed is the right way to do it. Maybe you should just say, okay, here's how far I can get. Let's pick a point here and go there.
Well, the question is, what does unpredictable exactly mean? If it's not
Right,
just you
but the problem, in the mathematical problem, instead of k being fixed, you want to design your walk so that for any particular time into the future, no matter what time they're looking at, that your location at that time is going to be as unpredictable as possible. And taking such a walk has turned out to be a very interesting mathematical exercise. More about this later, perhaps. Okay. Oh yeah, little application here. So the Vietnam draft lottery. I was a victim of this lottery. I had 3 years in the military. This is a picture of a congressman picking the first capsule. So what they actually did was they put each of the 366 possible birth dates into a fishbowl, starting with January 1st, ending with December 31st. And they mixed them around. And then this guy reached in and picked out one capsule at a time. And the first capsule became draft number 1, you go first. Not the time when you want to be first. And etc. I actually ended up number 90, which was not very good. But we can ask the following question. People were wondering whether this was really a random process, and we could ask the question, should you be suspicious if some month got 6 dates drawn out of it before some other month got any? Okay. But now from our previous experiment, you probably have an idea that the answer to this question is no. This is actually something you're likely to see. See, what actually happened, it's kind of interesting, and for those, maybe some of you here remember, this is a plot of the day of the year from January 1st to December 31st is written along the bottom. And from bottom to top is the order in which that number was picked. Okay? And at the moment, this looks like a sort of a reasonably random thing. But if you plot it by month, the plot looks like this. So what's going on here is that that heavy bar in the middle of each month is the average point at which birth dates in that month were chosen. And the bar on either end represents one standard deviation on either side. So it appears from this picture as if the months of September through December got chosen rather earlier, and because those were the capsules put last into the fishbowl, there was a complaint complaint that this is discrimination against people born late in the calendar, like me. I was a November baby, and in fact, there was a lot of hemming and hawing about this, and they didn't redraw for that year, but they used a different method succeeding years, so which seemed to be more fair. Actually, there's an interesting philosophical question about fairness here. I mean, what does it really mean to discriminate against people who were born in November? I didn't have any choice about what month I was born anyway, right? And here we're really heavily discriminating against people who were born on September 14th, right? I mean, every one of them is going to be number one in the draft list. I mean, I don't know. So I just want to say there's an issue here about what fairness means, as well as whether this was a statistical picture. Okay.
I heard another lecture on probability many years ago by Mark Katz, and he said that he had to testify in Congress as to whether this was statistically probable or not. And he said, as a probabilist, he couldn't criticize what the outcome was at all, even if it was highly improbable.
I'm going to address that very indirectly with the next slide. Okay. So.
Wasn't there a backstory here that the previous time they did a lottery was during World War II, and they spun it so hard that the drum broke, so they decided this time they would be very careful in spinning the drum?
I never heard that. I think they didn't spin the drum. In this particular case, they didn't spin the drum. I mean, you really saw they put the capsules into this fishbowl, and then they just stuck their hands in there like this to try to mix them up, and then they picked dates out. So the question about whether the chart that I just showed you should be suspicious depends, as Katz probably testified, on whether there is something, I mean, it's not surprising to see some months behaving quite differently from others. But it is the case that they put the late months in the bowl first. And it is the case that the 4 late months were the ones with the earliest choice. You put this fact together, and now it looks suspicious. I mean, so I really want to talk about what makes something look not random or suspicious. Right? So if you, it's not just that it's something which has low probability. Right? If you look at the New York lottery and you look at the last winning number, it's some crazy 7-digit number, whatever it is, 9-digit number. And what's the probability that that particular number would be chosen? Well, it's 1 in a million or whatever, 1 in a billion, whatever it is. But that doesn't make the whole drawing suspicious, right? Because there's nothing special about that number. So things that have extremely low probability are happening all the time all around us. That doesn't make life suspicious. What makes it suspicious is if something that has low probability, which could have been explained by some high probability. So I just have to tell you about my little crazy theory before we go on. And right, so we're looking for. So we would agree that if all of a sudden the New York lottery number was 0, 0, 0, 0, 0, 0, 0, 0, 0, everybody would really say, "Wait a minute, that's kind of funny. Is that really a random number?" There's a great Dilbert cartoon about this. There is a problem, though, and that is that this special significance has a subjective twist to it that we can't undo as humans, because every one of us can't, let me put it this way, none of us can explain why we're us and not somebody else. Okay? It's one of these great mysteries. Right? And therefore, right, there's always this possibility in our minds that there is a reason that I'm special and the rest of you, you just behave sort of like I expect you to. And, but suppose, for example, okay, suppose you dream that that particular number will win the New York State Lottery, and when you somehow, I've occasionally been able to capture things in memory, not a long number like this, but like a 2 or something like that. So you wake up this number, write it down on a piece of paper, and then later on in the day you find out it is the thing. So what should you think? Well, my theory is that, okay, so on the one hand, this is a 1 in 36 million. There's a lot more than that people in the world. There are billions of people in the world. So dreams with this likelihood are going to come true every day, many of them. So maybe you shouldn't be impressed. But still, it happened to you, right? So if you consider that there is a better than 1 in 36 million probability that dreams can come true, and that's not very much probability. You don't have to be a fanatic to believe that this has probability higher than that. I mean, that's not much. Right? Then my theory is that you're really entitled to believe that dreams come true. Right? I don't blame you. You might be. I think you're wrong, but I also think you're entitled to believe it. So that's the idea. Okay. Yes.
But isn't this also partly the explanation for people's reactions to cancer clusters, or to the issue about vaccination and mercury poisoning?
Oh yeah, yes, absolutely. And as is the previous stuff that I was talking about, saying that so part of it is your own experience is always written much larger than everybody's experience in general. And part of it is this whole idea about randomness and uniformity. Right? I mean, the stars are a great example. I mean, the stars, they don't look like random. They look like they make constellations and stuff. You know, they're... Yes?
Just a personal question.
Yeah.
Where do you stand on assigning probabilities to things that happen only once or a few times? Because in Kolmogorov would say, don't assign any probabilities to things. It doesn't make any sense.
Yeah, no. It's a difficult problem. My answer usually is that the best way, the only good way we have of assigning probability to a one-time event is to collect money for bets and see where the line is drawn. Right? I like to look at the line from NFL football and see what actually happens. And it's marvelous. It works extremely well. If you, the people who know most about it are betting the most money. Now, naturally, there is a bias toward people who actually have more money. There's a bias to people who are addicted to gambling and various other things. And there's also quite a bit of money in the pot from little people who don't know much about football, but just think that, you know, the Steelers are always a good team, so it's bet on the Steelers or something like that. So my advice, if you want to bet on football, well, my primary advice is not to, but the secondary advice is write down what you think the line should be. Okay. Say there's a big game coming up, a big college game coming up this weekend between the University of Georgia and the University of Alabama. And I don't know what the line is on this game. It's probably 10 or 12 points for Alabama or something like that. And but suppose I write down, I say, okay, I think the line should be Alabama -12. Okay. Now I go look and see what the actual line is. And the actual line is Alabama -14. So now the logical thing would be, aha, okay. So that means that they're even more fond of Alabama than I am. So I should take advantage of this and bet that way. But my theory is you should bet the other way. You should bet on the other side of the Las Vegas line for more your intuition. Because you're in the group that doesn't know as much about football as the heavy bettors. Okay? So your group has biased the line away from the smart people. You want to bet with the smart people. So if you always check your intuition and bet on the opposite side from your intuition.
Unless you think you're smarter than everybody else.
Unless you think you're smarter than everybody else about football. Exactly. Exactly. Okay. Here's a puzzle I devised, and after I devised it, I found out that my colleague Peter Doyle had devised the same puzzle independently. Yes?
I just want to say about that one, that concluding from the example you gave before, because of that improbable event happening to you, concluding that dreams do therefore come true, there's a good cautionary line in Aristotle where he says, it is very probable that in the course of life, very improbable things will happen to you.
I think I can use that quote. Thank you very much. And now I'm going to give you another take-home puzzle. And can you come up with a reason why this should be the case? So, in other words, Sarah's reasoning and Julia's reasoning were both correct, and they exactly cancel. And the question is, why do these two numbers come out exactly the same? And again, call on me later if you want to hear the answer, but I won't tell the whole group. Okay, we're getting down to end of time, probably. We're past it. I never asked how long I have. Okay. The committee of 10 people needs to select a chairperson, and they do it in blackballing rounds. Okay? So in each round, every member blackballs some other member. And so after one round, a bunch of the committee members are gone. They just leave the room. And they'll try it again. And eventually, maybe there's one person left. And that person is the chairperson. Okay?
Could be nobody's left.
It could be nobody's left, in which case they might have to do the whole thing again. But the question is, the question I'm asking is natural. What is, as the size of the committee goes to infinity, this does happen in some colleges, as the size of the committee goes to infinity, what is the limiting probability that there will be someone left standing from this process?
Blackballing is at random.
What?
Blackballing is at random.
Blackballing is uniform random. There's actually, I'll give you another version of this question, which you might find easier. Start with a large bucket of pennies, you know, and of pennies, and empty this bucket out onto the table. And then just remove all the pennies that have come down tails. All right. Put the heads pennies back in the bucket, shake it up, pour it out again. Remove all the tails. Keep doing it. Okay. Now, what's the limiting probability that you end up with one? That you end up with one? Clearly, that might happen or it might not happen. It might be that you get down to 2 and then they both flip tails and they're gone. Maybe you get down to 5 and they both flip tails and they're gone. And now this is the last bit of the surprise. Maybe some of you have seen this problem. My colleague Carl Pomerantz at Dartmouth found he had a student who found a very nice proof of what actually happens here. How much do you know what happens? You know what happens here? No? It turns out that this probability does not approach infinity. It turns out that, I mean, this most mathematicians find utterly bizarre. What's going on here? Can it be that no matter how many coins there are, the probability will keep fluctuating in a pattern?
It continues as n grows.
It continues to fluctuate.
It continues. As n grows.
As n grows, it continues to fluctuate. It never. And the funny part about it is that the first time someone thought about this problem, I'm told, they did some computer simulations. And the conclusion from the computer simulations was that it does converge. But the fact is it doesn't. So it varies just a little bit. According to the fractional part of the natural log of n, if you do it with the blackballing, or the log base 2 of n, if you do it with the coins.
Does that oscillation have this same amplitude, or does it just shrink slower than 1 over n?
It has the same amplitude. So that if you fix the fractional part of the log and then look at n's with the same fractional part, it does approach a limit. But that limit will be different for a different fractional part. Okay, so for example, if n is always in the coin problem, if n is always a power of 2, then it does approach a limit. Okay. You guys have had enough of this, so let me just wind up. When dealing with probability, some piece of advice: watch out for ill-posed problems. Watch out for probability versus expectation. Watch out for randomness. It's not the same thing as fairness. And watch out for the subjectivity of suspicion. There's more I could write down, but I think that'll do. And the only thing that can save you is stop, do a toy problem, and see if your intuition hasn't run off the rails. Okay, and thanks for coming.
Thank you much for your talk. Are there any questions?
Yes.
Well, I mean, you set us up, but I am curious. I mean, so there were several places where you promised us, if we asked, that you would tell us. I really can't do all of them.
I can't remember what they were, though.
I'm most curious about the 250,000.
Oh, yeah.
Totally countered.
Oh, yeah. So there's a number of proofs that Polia's urn has this property that the number of dollars in the smaller urn is uniformly random between 1.5 million. And here's one that I like. So because I'm a card player, I think of the following way. I have this deck of cards, and actually it's 999,998 cards. A million minus 2 cards. Now, make it minus 1. And what I want to do is I want to do a perfect shuffle with this deck. I want to get absolutely uniformly random shuffle. So, and I'm going to do it the following way. I'm going to take one card. Maybe it's the card on the top of the deck. Maybe it's the ace of spades. And put that down where my new deck is going. Then I'm going to take the next card, whatever it is, and I'm going to slot it with equal likelihood above the ace of spades or below the ace of spades. Okay. And then I'm going to take the next card off the top. Now there are actually 3 slots for the card. And I'm going to choose one of those 3 slots uniformly at random and stick the card in there. Okay? And the next card will have 4 slots. I'll pick one of those slots. Okay? So this is a legitimate way to get a perfectly uniform random shuffle. It's not a very easy way, but it's probabilistically correct. Okay? But if you think about it, it's exactly equivalent to the Polia urn, right? Because where you think of the cards above the ace of spades, well, actually the spaces above the ace of spades, as the dollars in the first urn, and the spaces below the ace of spades are the dollars in the second urn, right? So if at some point you've got 5 spaces above the ace and 10 spaces below, the next card will go more likely below with probability 2/3. Okay? So we've reproduced the Polia urn. And now all we have to do is take the final shuffled deck and count the number of the distance from the ace of spades to the closer end of the deck. That'll be the amount of money in the smaller urn. Maybe plus $1. And but if it's a randomly shuffled deck, that ace of spades is exactly uniformly, equally likely to be any place in that deck. And that gives you the uniform. So that's my way. There are other ways. There are other ways. Yes.
Returning to your problem with the dream, how does the ESP experiment of a couple of years ago strike you?
So I remember there was an ESP experiment which was so carefully designed and so statistically convincing that somebody, I don't know who it was, some well-known statistician, said about the experiment, there are only 2 conclusions I can draw. One of them is extremely unlikely, and the other one is extremely unpleasant. If I understand this right, the extremely unlikely one is that ESP exists. The The unpleasant one is that this experiment was deliberately rigged because it looked so convincing. Yes, here.
I'd like to understand ill-posed problem.
Mhm.
Is that primarily sample space not defined, or are there other? I
Sample-
would think that that's the most.
I agree with you. In my experiment, at
the beginning, that
in my
was the
experience,
problem.
yes. In my experience, the problem often is that you don't exactly have specified what is the experiment, what is the sample space. You specify what is the sample space, which I've done in all of my problems here, then you kind of reduce the intuition thing to something where at least you know exactly what's being asked. And I like that kind of problem because I'm a probabilist and not a sociologist.
Right, and that was the sense in which the examples you started out with were ill-posed. No.
Yes, but there are other possibilities for ill-posing a problem. And one of them is, of course, if you're talking about a one-time event, this probability is not there as a defined probability. There could be a problem there. There might be some other feature of the problem that isn't correctly or exactly posed. There's a version of this this boy-girl thing where the boy is born on the second Tuesday of the month or something like that. You get an even more bizarre answer. But if you try to actually set up an experiment where that's the answer, it can be done. Pretty bizarre.
In the boy-girl problem, since you just mentioned it,
Yeah.
you said that there are a lot of ways to phrase the problem where the answer would be half.
Right.
So a lot of it comes down to the question of how it is that you receive the information and how you're used to receiving information. How many of the problems that you've gone through here can be traced back to that? That is something about human psychology and the way we're constructed to build or understand probabilistic situations from experience rather than because somebody told us that the probability is
Probably a lot of them. Right. I mean, it's so yes.
Most or maybe not all.
Some of it comes from experience with people asking you questions and knowing that they have a kind of a trap in mind, right? So there's experience of real life, and there's also experience with puzzles, and they both have.
So you're not the one to answer this question.
Right, yes.
Too much experience.
I'm probably not the one, yeah.
Yes.
Yes.
So if we're going back and retrieving answers, the aliens abducting the girls and the boys.
Okay. So who's got an answer for that? What's the probability that the last person chosen by the aliens was a woman? There are 5 women and 5 women and 3 men. Your intuition will be higher than the 5 A's. Any other intuition? Well, actually, there's a. So this problem was posed by Martin Gardner years ago in a different version, and he correctly stated that the answer is half. And however, Gardner waved his arms around and said that you can prove this by induction, blah blah blah. He didn't offer a proof, intimating that this is something for the mathematicians to worry about. It's just curious that the answer is a half, no matter what the numbers are. 45 women and 16 men, the answer is a half. Okay. And but I think there is a nice way to see that it's a half. And I'll tell you what it is. You very often the way you can answer the questions is by rephrasing the question in a slightly different way, just changing where the probability goes in or something like that. And here's what we're going to do. When the saucer appears over the house, instead of just beaming up each person randomly, it takes all the people in the house and puts them in a random order. It lines them up. Bing, 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 like that. And then it just beams them up from front to back until it hits the opposite sex and puts that one back, and it takes off. And the next saucer comes down and re-randomly lines up the people, and then it takes people. That's the same thing, right? I mean, choosing randomly is the same thing as choosing an order and then choosing from that order from the top. Okay? So here's the catch, is that the next to the last flying saucer will be ordering the people as follows: either all males and then all females, or all females and then all males. That has to be the way the next to the last saucer lined them up. Because that's the only way that it's going to be leaving only one sex behind it. Okay? But now if we've got a bunch of people and we randomly order them, the probability that it's men in front, women in back is exactly the same as women in front and men in back. Right? You can just reverse the order of the line to see this. So it's a half. So I think that Martin missed that one. He didn't miss much, though. Him and his readers got him. Yes.